So in this video, what we're going to be talking about is how we can use derivatives to come up with equations of lines tangent to curves and lines normal to curves. So before we do that, we're going to have to take a step back in the Wayback Machine here and go probably back to like 7th, 8th grade when you guys learned how to create an equation of a line. And so I'll ask the question to the YouTubers out there, what two things do you need to form an equation of a line? Anyone? Bueller? All right, well, the two things you need are a point and a slope. Okay, so let's pretend that we got a point right here. We'll put it right here. Our y value, we'll call that f of a. Our x value, we will call a. Pretend we got some line that goes through that with some slope m. Okay, so in this case, the point that we have is x is a, y is f of a, and the slope is that value m. Now f of x is going to be given by this curve right here. So if we have a slope and we have a point, we can use an equation called the point-slope form to determine what the function is, and that will be that f of x minus f of a is equal to that slope times x minus a. Now if we rearrange this, we'll just get that f of x is equal to m times the quantity x minus a, then plus f of a. So this is kind of like an end-all be-all equation that can tell us the slope of a particular line. Now let's pretend instead that I want a slope of a line normal to a curve at this point. Now remember the word normal, what does that mean? Well, normal in math speak means perpendicular, okay? So if we want an equation for a line perpendicular right here, the slope of this line is given by what? Well, you might remember this is the negative reciprocal, so this slope would be -1 over m. So if we wanted to develop an equation for a normal line, that would be very similar to the equation that we used right here, but instead our slope is just going to be different. Our point is going to be exactly the same. The point is still going to be a comma f of a, but now the slope is going to be -1 over m. So the normal line, we'll call that fn for normal. That will be -1 over m times x minus a plus f of a. So these are kind of like end-all be-all equations that you can use to find equations of tangent and normal, or to find equations of lines and then normal lines. So what we talked about so far in this particular unit is the concept of the derivative and how to calculate derivatives. So recall what a derivative is. A derivative is a slope of a line tangent to a curve. So in calculus, when we're asked to find equations of tangent lines, the slope of that tangent line is going to be given by the derivative, and that's the slope that we will use to plug into these equations to calculate equations of tangent lines and normal lines. So let's look at a quick example of this. So let's look at this problem. All right, find an equation of the line tangent to the curve y equals x cubed minus 2x squared plus 1 at the point x equals 1. Okay, so the two things we need, remember, are point and a slope. Let's do the point. That one's easy. Well, what's the x value we got? It's 1. So therefore, if we want to find the equivalent y value, what do? Well, we just plug x equals 1 into the equation for y. So that'll be 1 cubed minus 2 times 1 squared plus 1. We do all that out. We'll get 1 minus 2 plus 1. We'll end up with 0. Oh, that's convenient. All right, so that's our point right there. Now, if we want the slope, how are we going to get the slope? Well, remember what I told you. We were looking for an equation of the line tangent to the curve. So the slope of a line tangent to the curve is what? It's the derivative. That was supposed to be an exclamation point. All right. So what we need to do is to evaluate, in this case, dy dx at x is equal to 1. Okay? So first of all, let's find what dy dx is. now that we know our handy-dandy power rule, we can evaluate this derivative. So try to do it on your own first. Pause the video, and then we'll see if you were right. Okay, so if we're going to evaluate this, this derivative would be 3x squared minus 4x. Then the derivative of a constant is just 0, so it would just be that. So at x is equal to 1, we would have that dy dx, just plug 1 into the equation, would be 3 times 1 squared minus 4 times 1, which would just give us negative 1. Okay, so we got our slope, now we got our point, so all we got to do to figure out the equation of this line is to just plug it in to the point slope form. So we would get that the equation of our line, y tangent, if we use the same equation we had before in the previous slide, it would just be equal to our slope, negative 1, times x minus 1, remember 1 is our x value, then plus f of 1, which we found to be 0. So the equation of this line would simply just be negative x plus 1. Okay, so let's go into Desmos real quick. And we already have this equation plotted right here. So don't worry about all this other stuff on there. We'll go over this later. But we got our equation right here. So if we plug in that function y equals negative x plus 1, and we zoom in on the point right where x is equal to 1, doesn't it look like that black line is completely tangent to the curve right at that point? So I would say we calculated this one correctly. Okay, so let me remove that, and now let's go back real quick. So on the next example, let's look at how we would calculate a normal line. So you saw what we did in the previous example. Okay, we know again that our point is going to be exactly the same because we're looking at the same point. That's going to be 1, 0. The slope is going to be different. So why don't you figure out what the slope of the normal line is? Try to determine what the equation for the normal line is on your own. Pause the video and we'll see how you do. Okay, well, remember our slope before, the slope of the tangent line, we'll call that m tangent, from the previous case was negative 1. So the slope of this will be negative 1 over that tangent line slope, which will just be negative 1 over negative 1, which is just 1. All right, so if we plug that into the normal line equation, we'll get the normal line will be that slope 1 times x minus 1 plus our value for f of 1, which would be 0. So all we get in this case is that this equation would be x minus 1 would be our equation for that normal line. So let's go back into Desmos and see how we did. If we plug in x minus 1, whoa, look at that red line that just showed up. Doesn't that look like that is pretty much normal to that curve? If we plug in the previous line we found, negative x plus 1, now we put those in, doesn't it look like the tangent and the normal line are perpendicular to each other? Well, it's because they are, okay, because we calculated all of this correctly. Now, to go into a bit of a description of what these other equations up here mean, if we zoom out here, you'll see I got two equations right here, this one and this one. Now, t of x represents our equation for a line tangent to the curve, and notice that I'm just plugging in that point slope equation that we went over in the first slide of this video. In this case, fp of x, the subscript p stands for prime. That's the derivative of our function f of x. So if I'm looking at fp of a, I'm saying what is the derivative of our function at x equals a, which remember, a derivative means the slope of a line tangent to the curve. So fp of a is giving me the slope of my tangent line. So if I just plug that into the point slope form, I get an equation for the tangent line. Likewise, n of x is my normal line. What's the only difference? And let me click on this so it can be a little bit bigger. What's the only difference between the equation for n of x and the equation for t of x? Well, you'll notice that they both use the same point, that point A comma f of A, but the difference is the slope is different. In this case, the slope is the negative reciprocal of this slope right here. Okay, so why did I create these two functions? Well, I created them to show you that if the math is right, it will be right all the time. So if I erase all this stuff, and then I show these 2 points, look at the 2 lines that show up. That's our tangent line and our normal line that we had before. And if I move our slider for A, in this case A represents our x value, you'll see that no matter where I go, these lines stay tangent and normal to the curve. So these equations work everywhere. The only place where we have an issue is when we get to the horizontal tangent, because then our other tangent is vertical, and we know that vertical tangents, that equals bad news. So that's why the normal line disappears right there, but then it just reappears back when we have a non-horizontal tangent line. So anyway, hope you enjoyed this video, and so come to class tomorrow with questions on this stuff. If you don't have any questions, we'll start working on a few more examples.